You found a quiet place, just for you. Here, the noise of the world fades and the universe begins to whisper. This video isn't a lecture, it's a journey, a gentle one, through the strange and beautiful truths of quantum reality. There's nothing you need to do now, no need to understand everything. Just let the words settle softly, let your thoughts slow down, and your body grow still. Because sometimes the best way to feel lighter is to zoom out, far out. And remember that at the smallest scales, your worries dissolve. Let's begin. Chapter 1. You are mostly empty space. Close your eyes for a moment and picture your hand resting gently on your chest. You feel its weight, the warmth of skin on skin, the reassuring presence of something solid and familiar. And yet, beneath that comforting sensation lies a truth so strange it borders on the unbelievable. You are almost entirely empty. At the most fundamental level, your body, and indeed everything around you, is composed of atoms. Atoms make up the cells in your skin, the calcium in your bones, the neurons in your brain, and yet the atom itself is a ghostly structure. Imagine an atom scaled up to the size of a football stadium. At its center, a nucleus, composed of protons and neutrons, would be no larger than a grain of rice sitting on the 50-yard line. The electrons, dancing around this central speck, would be orbiting somewhere near the outer bleachers, and between them, almost nothing. Vast, yawning space. It's not poetic exaggeration, it's measurable fact. Over 99.99999% of the volume of any atom is empty space. And since you are composed of atoms, that means you too are mostly space. The chair you sit on, the blanket you pull over yourself at night, the ground beneath your feet, they're all built on that same improbable scaffold, fields of emptiness dotted with infinitesimal points of energy. It would be reasonable to ask, if we're mostly empty, why do we feel solid? Why don't we fall through floors, dissolve into mist, or pass through walls like phantoms? The answer lies not in the material of our bodies, but in the forces that govern them. When you press your hand against the table, what you're truly experiencing isn't matter touching matter. It's electromagnetic repulsion. The electrons in the atoms of your hand resisting the electrons in the atoms of the table. The closer they try to get, the more forcefully they push back. It's like trying to force the north poles of two magnets together. They never really connect, but the sensation of resistance is enough to convince us of solidity. In that moment, you're not touching the table. You're floating above it at the scale of angstroms, separated by fields of invisible energy. And yet, somehow, all of this emptiness is responsible for the physicality of everything. This paradox, that something so apparently solid is made almost entirely of void, sits at the heart of quantum mechanics. It teaches us that substance is not a requirement for stability. Structure arises from fields, probabilities, and force interactions. The universe, in its genius, builds form not from bricks and mortar, but from patterns of absence and flickers of presence. The nucleus itself is a dense mystery. If you could isolate just that central grain of rice core and compress all the nuclei from every atom in your body into one space, you'd be left with something impossibly small and impossibly heavy. In fact, if all the empty space were removed from all the atoms in all the people on Earth, humanity could fit into the volume of a sugar cube. Just imagine, 8 billion lives, memories, thoughts, and dreams, reduced to something you could hold between your fingers. This idea isn't just a curiosity. It's an invitation to understand that reality operates very differently from how we perceive it. Our senses evolved to navigate a middle world, one that lies between the scale of galaxies and quarks. We don't feel the atom's emptiness because we were never meant to. But that doesn't make it any less true. At the quantum level, the stuff of the universe is not stuff at all. Particles are not tiny marbles. They are excitations in underlying fields. The electron is a ripple in the electron field. The photon, a ripple in the electromagnetic field. These fields stretch across space, present everywhere, always fluctuating. Particles are just manifestations of energy, rising and falling in a restless, probabilistic sea. The illusion of solidity is an emergent property of countless interactions, repeating instability, giving rise to something we interpret as form. And so when you feel your hand, or see your reflection, or lean against a wall, you are interacting not with matter, but with forces, energies, and probability distributions. You are not touching reality, you are being repelled by it. Every moment of contact is a negotiation between clouds of charge and waves of possibility. This might sound disconcerting, but there's something quietly reassuring about it. If you're mostly empty, if solidity is an illusion, then maybe the pressure you feel in life, the emotional weight of the world, is also built on perceptions that don't reflect the full truth. The universe does not demand solidity for meaning. It allows structure to emerge from uncertainty. It makes identity from impermanence. The emptiness in your atoms is non-flaw. It's the very thing that allows you to exist. If atoms were packed tight like solid spheres, life as we know it would be impossible. Chemical bonds rely on the space between electrons. Interactions happen because particles have room to dance. Consciousness, too, may rely on the fluidity of these ever-changing states. The gaps create the music. The silence creates the shape of the sound. Even now, the atoms in your body are mostly idle. Space between them is vast, and the particles within them are ghost-like, popping in and out of energetic states, influenced by fields and forces that never stop. You are not a static sculpture. You are a storm held in pattern, a fluctuating field of possibility, barely held together by the threads of physics. And yet, here you are, breathing, blinking, wondering. The atoms in your body are ancient. Many were forged in stars long dead, scattered through the void by supernovae, swept up into the dust cloud that became our solar system. These same atoms once drifted through galaxies, passed through comets, maybe even composed other forms of life. Now they assemble you, a temporary configuration of energy and space, one that thinks and dreams and feels. To realize that you are mostly empty space is not to diminish you. It is to reveal your connectedness to everything. You are part of the very framework of the cosmos, woven from its same raw principles, animated by the same subtle rules. So when the day feels heavy, when stress creeps into your mind like a weight on your chest, remember this: you are weightless, not in feeling, but in form. The atoms of your body hold no grudges. The particles in your brain don't know anxiety. They move, they vibrate, they interact, but they do not judge. They are as free as space itself. You are not solid. You are a miracle of structure in a sea of emptiness. And yet, somehow, you are here. And that's more than enough. Chapter 2. Nothing is ever truly still. Everything in the universe is in motion. From the great arcs of galactic rotation to the internal vibrations of molecules in a drop of water, motion is not the exception, but the rule. It defines the very nature of physical reality. But in the world of quantum mechanics, where the building blocks of matter reveal their most intimate behaviors, motion takes on a new, unexpected character. It never stops, not even in the coldest, quietest, darkest corners of existence. At absolute zero, the theoretical point at which all classical motion ceases, one might expect the universe to fall completely silent. No vibrations, no energy, no motion at all. And yet, even there, particles still shiver, not out of warmth or external energy, but because nature itself does not allow them to be still. This phenomenon is known as zero-point energy. In quantum mechanics, particles do not simply sit still at their lowest energy level. Instead, they retain a small, irreducible amount of motion. Built into their very being, This is not just theory. It's observed, measured, and accounted for in precision physics and high-technology instruments. Even in a perfect vacuum cooled to a fraction of a degree above absolute zero, atoms still jiggle. They still hum. They still move. This isn't because of thermal agitation or chaotic interference. It's because of the fundamental uncertainty at the heart of the quantum world. According to Heisenberg's uncertainty principle, we cannot know both the position and the momentum of a particle with perfect precision. The more precisely we know one, the less precisely we know the other. As a result, particles can never sit entirely still. If they did, their momentum would be known exactly, zero, and that would violate quantum law. This means that stillness, as we intuitively understand it, is not a real physical state. It's an illusion, a simplification that helps us make sense of the macroscopic world. When we see a book resting on a table, we think of it as immobile, but the atoms within its cover are vibrating. The molecules in its pages are rotating, stretching, bending. Its electrons are moving in cloud-like orbitals, and its protons and neutrons are quivering with quantum fluctuations. The book is alive with motion, invisible though it may be. And so are we. Even in moments of deep rest, your body is never static. The atoms in your skin, blood, bones, and brain are in constant motion. Molecules stretch and spin. Ions drift across cell membranes. Neural signals flash with electrochemical pulses. You are a symphony of movement, layered, complex, and ceaseless. Every breath you take sets billions of particles into motion, even as you lie still. But beneath even this biological activity lies a deeper kind of motion, the trembling of particles that can never quite be pinned down. A kind of soft quantum turbulence that keeps the machinery of existence from grinding to a halt. This motion is not noise. It is not chaos. It is structure. It is the architecture of matter in its most essential form. Without this motion, atoms wouldn't behave the way they do. Electrons might collapse into nuclei, destroying the stability of the periodic table. Chemical bonds might fail to form. The delicate dance of particles within stars, responsible for producing light and elements, would grind to a halt. Life, chemistry, even time itself would cease to have meaning in a perfectly still universe. The persistence of quantum motion has real-world consequences. Consider the Casimir effect, one of the more visually striking consequences of zero-point energy. When two uncharged metal plates are placed extremely close together in a vacuum, mere nanometers apart, they attract each other, not due to magnetism or gravity, but because the quantum fields between them behave differently than those outside. This isn't a theoretical curiosity. It's measured in laboratories and used in nanotechnology designs. Even the space between objects, supposedly empty, carries the signature of motion. What we often consider as vacuum is not truly empty either. It teems with ephemeral particles flickering into and out of existence. This restless energy, known as vacuum fluctuation, is another reminder that motion is not just a property of things, but a feature of space itself. Quantum fields ripple even in the absence of mass or energy. This redefinition of stillness is not just scientific, it's philosophical. If stillness doesn't truly exist, if even emptiness is animated, then perhaps we must rethink what it means to rest. Rest is not the absence of motion, but the presence of equilibrium. A state where forces balance, where change becomes rhythmic instead of chaotic. When you lie in bed at the end of the day, you may feel still, but within you, electrons shift, water molecules vibrate, cells communicate through subtle exchanges of ions. These processes are not distractions. They are you. You are not separate from the quantum dance. You are one of its countless expressions. The ancient idea of stasis, of permanence, of immovable states, has been replaced in modern physics with a more nuanced view: dynamic equilibrium. The universe is in constant flux, but that flux can be patterned, harmonious, and stable over time. Like the surface of a calm pond rippling gently under the breeze, the movement never truly ends, but it can exist in a steady state. In this view, your mind, your thoughts, memories, emotions are not disruptions in stillness, but extensions of this same continuous motion. Brain activity is governed by ion gradients, neurotransmitter shifts, and quantum interactions in protein structures. Even consciousness, however mysterious, may be rooted in dynamic fluctuations at the edge of perception. And while we do not yet fully understand the relationship between quantum mechanics and the mind, what we do know is enough to reshape how we think about ourselves. You are not a static being waiting to be acted upon. You are motion, you are rhythm, you are a local expression of a universal beat. When stress weighs down the body and mind, it can feel like the world is stuck, like nothing is moving forward. But beneath that feeling lies a deeper truth. Even in silence, even in darkness, even in despair, there is always motion. Motion within your body, motion within your atoms, motion within the universe itself. To understand this is not merely to study science. It is to recognize your participation in something ongoing, something ancient, something unbroken. The same laws that keep particles from freezing in place are the ones that make your body breathe, your heart beat, your thoughts unfold. And so if you ever find yourself lost in the stillness, burdened by quiet, frozen by uncertainty, remember that you are not truly still. You are vibrating, living, shifting within patterns of endless motion that stretch back to the birth of the cosmos. Stillness, it turns out, is just motion in disguise. Chapter 3. Particles can be in two places at once. In the classical world, the world we move through every day, objects have well-defined positions. A book rests on a shelf. A pebble lies at the bottom of a stream. A leaf drifts gently to the forest floor. These things are where they are and not elsewhere. This certainty is not just practical, it's intuitive. It forms the foundation of how we perceive existence. But as we step into the quantum world, that sense of certainty begins to unravel. At the quantum scale, particles such as electrons, photons, and even entire atoms can occupy a strange state known as superposition. In this state, a particle doesn't simply exist at a single point. Instead, it inhabits a range of possible positions simultaneously. In a very real and measurable sense, a particle can be in multiple places at once, until something observes it. This is not science fiction. It is science, tested and retested through decades of experimentation. One of the clearest demonstrations of superposition is the now famous double-slit experiment. Here's how it works. Imagine firing a beam of electrons, one by one, at a barrier with two narrow slits. Behind the slits is a detection screen that records where the electrons land. If electrons behaved like tiny marbles, we would expect them to go through one slit or the other, forming two bright bands on the screen. But that's not what we observe. Instead, we see an interference pattern, a series of alternating bright and dark fringes, like ripples overlapping on the surface of a pond. This pattern reveals something astonishing. Each electron is interfering with itself. It acts not as a particle, but as a wave. It does not choose one slit or the other. It passes through both. Only when a detector is placed to monitor which slit the electron travels through does the interference pattern disappear. The electron chooses a path, and the wave-like behavior vanishes. The act of observation collapses the superposition. Measurement changes reality. This bizarre yet repeatable phenomenon lies at the heart of quantum mechanics. It tells us that quantum particles are not objects in the conventional sense. They are probability distributions, described by what physicists call a wave function. This wave function does not point to a specific location or outcome. Instead, it provides a map of probabilities, a guide to where the particle might be found, and with what likelihood. Before measurement, all these possibilities coexist. The particle is not here or there. It is both. It is not up or down. It is some weighted blend of both. Reality at this level is not composed of fixed points, but of layered uncertainties, delicately balanced until an observation is made. This concept doesn't only apply to position. Quantum particles can be in superpositions of energy levels, spin orientations, or polarization states. They can be both excited and not excited, both spinning clockwise and counterclockwise, both passing through one slit and the other. This isn't abstraction. It's been verified experimentally in labs around the world. It also scales. Superposition is not limited to electrons and photons. Scientists have placed entire molecules, many thousands of times more massive than a single particle, into superposed states. Under isolated conditions, these larger systems behave in the same ghost-like way. They can take multiple paths simultaneously. The line between the quantum and classical world is not a wall, but a gradient, shaped by a phenomenon called decoherence. Decoherence occurs when a quantum system interacts with its environment, light, air molecules, or even just thermal noise. These interactions cause the fragile superposition to collapse into a single classical outcome. This is why we don't see cats in two places at once, or people phasing through walls. The systems around us are constantly entangled with their surroundings, forced into definiteness by sheer complexity. Still, the implications of superposition are vast. In quantum computing, for example, bits of information, called qubits, can exist in the superposition of 0 and 1. Rather than being limited to one binary state at a time, qubits allow for many states to be processed in parallel. This promises exponential gains in computational power for certain kinds of problems, such as factoring large numbers or simulating molecular interactions. But beyond its applications, superposition challenges something deeper: our understanding of presence. If particles can be in multiple states until observed, then the sharp distinction we draw between what is and what could be begins to blur. The quantum world suggests that potential is just as real as actuality, until it isn't. This realization has philosophical weight. It hints that the universe is not made only of things, but of possibilities, and that reality may not be something we uncover, but something that crystallizes through our participation in it. There are many interpretations of what this means. Some physicists argue that superposition is just a mathematical tool, useful but not literal. Others suggest that all possible outcomes occur in separate branches of a multiverse, each a real and distinct reality. Still others maintain a more cautious stance. Superposition is real, but how we interpret it remains open. Regardless of interpretation, the phenomenon itself is undeniable. Particles truly behave as if they occupy multiple locations or states at once. And when we attempt to isolate, observe, or control them, we influence the outcome. Even more intriguingly, quantum entanglement, the topic of a later chapter, can preserve superposition across distance. Two particles, prepared together, can share a single wave function, even when separated by great lengths. Measurement of one instantly determines the state of the other. Superposition, it turns out, is not just local. It can span the void. So what does it mean, practically, to say a particle can be in two places at once? It means that beneath the surface of the solid world, there is a hidden flexibility. That certainty is a product of interaction. That observation is not just passive viewing, but an act of definition. The world is not waiting in place, fully formed for us to discover it. It is unfolding, responding, collapsing into structure only as we engage with it. This may seem unnerving, but it can also be oddly reassuring. If the foundations of matter are not static but fluid, then so too are the limitations we often place on ourselves. Superposition tells us that the universe allows, at its very core, for uncertainty, for potential, for duality. You are not confined to a single version of yourself. You are, in a sense, a superposition of choices, histories, and futures. Not all at once, but perhaps not far from it either. This doesn't mean that we live in multiple realities or that our every decision spawns infinite worlds. But it does mean that the universe, as far as we can tell, is built to accommodate possibility. It does not rush to finality. It holds space for potential. A particle can be in two places at once. And though you may never physically split into duplicates and explore both paths at the same time, the idea itself offers a gentle comfort. You are part of a reality that does not demand immediate answers. It allows space for the in-between, for the undefined, for the not yet decided. And in a world that often pushes us toward rigid outcomes, that quiet truth may be one of the most liberating of all. Chapter 4. You've never really touched anything. Touch is one of the most convincing of our senses. It gives us a sense of presence, of grounding, the pressure of your feet on the floor, the support of a chair beneath you, the warmth of another person's hand. These experiences seem to confirm that we are interacting physically with the world, that we are in contact with something real. But here's the truth. At the atomic level, you have never truly touched anything. It may sound unbelievable at first, even paradoxical, but this statement is not metaphorical. It is a precise conclusion drawn from the physics of how matter interacts at the smallest scales. What you feel as touch is not the intermingling of atoms or the contact of surfaces. It's the result of electromagnetic forces acting at incredibly small distances, forces that ensure your atoms and the atoms of the objects around you never truly collide. Let's break this down. Every object you can see, hold, or feel is made of atoms. Atoms are composed of a central nucleus surrounded by a cloud of electrons. These electrons are negatively charged. When you bring two objects close together, say your fingertip and a tabletop, the electrons in your skin approach the electrons in the table, but electrons do not like to share space. Because like charges repel, your electrons and the table's electrons begin to push against one another. This electromagnetic repulsion ramps up as the two sets of atoms approach. You can think of it as an invisible cushion of force that gets stronger the closer you get. The result? The atoms never actually touch. Instead, they hover apart at a tiny, subatomic distance, held at bay by the sheer strength of the repulsion. What you experience as pressure or solidity is not physical contact. It is your brain interpreting these repulsive forces as resistance. Your nervous system detects the deformation of skin and the activation of pressure-sensitive receptors. Those receptors don't signal direct atomic contact. They signal the force being exerted against them. The result is a sensation that feels immediate, intimate, and yet, fundamentally, it's an illusion built from force fields. This illusion is incredibly consistent. Every time you press a key on your keyboard, place your hand on a doorknob, or walk barefoot on grass, you are experiencing an array of electromagnetic interactions. The Pauli exclusion principle, another quantum rule, plays a critical role here too. It prevents electrons from occupying the same quantum state within the same system. That principle, combined with electromagnetic repulsion, guarantees that atoms maintain their personal space. It's not optional, it's built into the fabric of reality. Interestingly, this separation is essential to the very concept of matter as we understand it. If atoms could simply pass through each other without resistance, nothing would hold its shape. There would be no boundaries, no solidity. The structural integrity of objects, of people, is maintained by repulsion. That which keeps you from touching something is the same force that keeps you from falling through the floor. In fact, the strength of these interactions is profound. Electromagnetic repulsion between atoms is many orders of magnitude stronger than gravity at that scale. While gravity shapes planets and stars, It is electromagnetic force that sculpts the everyday experience of contact. This force is why a spoon holds its form, why a window pane remains intact, and why your body can support itself against a chair. Without it, there would be no resistance, only free fall through layers of matter that offer no opposition. Even when it feels like something sharp, like a needle or a thorn, has pierced your skin, what's happening is still governed by forces, not fusions. The atoms in the needle do not merge with the atoms of your body. Instead, enough force is applied to separate molecular structures, causing biological damage and triggering pain receptors. But still, the atomic cores remain apart. The electrons continue to enforce their invisible boundaries. The field of scanning tunneling microscopy offers a visual testament to this. These tools allow scientists to image individual atoms by bringing a needle-like probe extremely close to a surface, just a few angstroms away. Electrons tunnel across the tiny gap due to a quantum phenomenon, allowing researchers to map out atomic structures. But even in this high-precision contact, the probe never actually touches the surface in the traditional sense. The interaction is one of proximity, not penetration. Chemical bonds, too, are governed by these principles. When atoms bond, they do not merge into one. Instead, their electron clouds overlap in very specific ways, sharing energy and space within allowed parameters. Covalent bonds, ionic attractions, van der Waals forces, all are variations of interaction, not fusion. There is intimacy, but not contact in the classical sense. In rare and extreme cases, such as nuclear fusion, atoms do get close enough for their nuclei to interact. But this requires immense energy, like the heat and pressure found in the core of stars. Fusion overcomes the natural repulsion between positively charged nuclei using brute force. And even then, it's not so much touch as it is transformation. The particles don't survive the encounter unchanged. They merge into something new. We can also appreciate the complexity of non-contact through the lens of material strength. Why does steel resist deformation? Why does glass shatter instead of bending? These properties arise not from solid blocks of touching matter, but from highly organized electron arrangements. Crystalline structures, lattice networks, and molecular geometry all stem from how atoms and electrons interact without touching. Even in your own body, at the interface of every sensation, between nerve ending and stimulus, between muscle and object, what's happening is a finely tuned field of repulsion, governed by ancient laws that predate life itself. You are constantly negotiating your way through the physical world by hovering fractions of nanometers above it, supported by nothing but invisible forces. This boundary, this inability to touch, redefines what it means to interact. It suggests that interaction is not based on proximity alone, but on influence. You don't need to touch something to affect it. Forces can act across space within limits. The world is stitched together not by contact, but by response. Matter responds to matter through the invisible hands of quantum rules. It's a humbling idea that every experience of solidity is a kind of negotiated resistance, that what we perceive as the hardness of a stone, the smoothness of glass, or the warmth of another person is a message, transmitted not by merging atoms, but by the structured push of fields against fields. So when you rest your hand on the table beside you, remember, your atoms are floating above its surface. Not far, but far enough that, in absolute terms, contact never happens. What you feel is not a collision. It is a conversation, a balance of opposing forces that prevents fusion and maintains form. This understanding doesn't diminish the richness of our experiences. On the contrary, it enriches them. It reveals that reality is more delicate and more intricate than our senses suggest. That the world is not coarse, but woven. Not hard-edged, but humming with invisible order. You've never truly touched anything. but you've influenced everything you've come near. And in a universe governed by interaction, not contact, that's more than enough. Chapter 5. Reality doesn't exist until it's observed. In classical physics, reality is objective. A ball falls whether or not you watch it. A planet orbits its star with or without eyes to witness it. The universe in that model is a machine running on predictable laws, indifferent to observation. But in the quantum realm, this picture begins to dissolve. Here, at the smallest scales of matter, the act of observing doesn't just reveal reality, it helps define it. This strange principle arises from one of quantum mechanics' most unsettling features, the idea that reality doesn't exist until it's observed, at least not in any definitive, measurable form. Prior to measurement, particles such as electrons and photons do not have fixed properties. They exist in superpositions, multiple potential states at once. It is only through observation, through measurement, that one of those possibilities becomes real. This isn't philosophy. It's a result backed by countless experiments. The double-slit experiment is perhaps the most famous illustration. When particles are set one at a time toward a barrier with two slits, and no one watches to see which slit they go through, an interference pattern appears on the detection screen beyond. It's as if each particle behaves like a wave, passing through both slits simultaneously and interfering with itself. But the moment you set up a detector to observe which slit the particle passes through, the interference pattern vanishes. The particle chooses a path. The wave-like behavior collapses. A measurement has been made, and in doing so, the system has been forced into a definite outcome. The act of observation has changed reality. This isn't because the detector nudges the particle or disturbs it in some crude mechanical way. It's because observation in quantum mechanics means interaction with the system, and such interaction reshapes the wave function, the mathematical description of all possible states. Until this interaction occurs, the particle isn't here or there. It's both, and neither. It simply exists in a probability cloud. This concept is formalized in what's known as the Copenhagen interpretation of quantum mechanics. In this view, a quantum system has no definite properties until measured. The observer doesn't just watch. The observer collapses the possibilities. Measurement doesn't uncover reality. It helps create it. Alternative interpretations exist. Some, like the many worlds interpretation, suggest that all possible outcomes do occur, but in separate, branching universes. In that view, the observer doesn't collapse the wave function, but becomes entangled with it, splitting into multiple realities with each possible result. Others, such as pilot wave theory, attempt to preserve an objective reality while explaining quantum behavior as driven by hidden variables. Yet no matter the interpretation, experiments consistently show the same result. Observation matters. Systems behave differently depending on whether they're being measured. This observation dependence is not a flaw in our instruments or a temporary artifact of incomplete understanding. It is built into the equations of quantum mechanics. And it shows up not just in electrons and photons, but in atoms, molecules, even in systems large enough to be nearly visible to the naked eye. Consider the phenomenon of quantum entanglement, where two particles become linked such that the state of one instantly determines the state of the other, even across vast distances. If one is measured, the other's state becomes defined, no matter how far apart they are. It appears as though measurement at one location influences reality at another faster than the speed of light. Again, observation defines outcome. It brings an indefinite system into sharp focus. This leads to an uncomfortable implication. If reality depends on observation, then what does it mean to exist unobserved? What is the state of the moon when no one is looking at it? Does it still exist in a definite place? Einstein famously objected to this idea, remarking, "I like to think the moon is there, even if I am not looking at it." But the quantum world doesn't bend easily to such intuitions. While macroscopic objects like moons and planets are constantly interacting with their environments, effectively being measured by everything around them, quantum systems are fragile. They can remain in superposition until disturbed. In isolated conditions, a single atom or photon can exist in this probabilistic limbo for long stretches of time. This raises a broader question: what exactly qualifies as an observer? Does it require consciousness, a brain, or just any kind of interaction with a larger system? Most physicists lean toward the latter. Observation, in the quantum mechanical sense, is not about human awareness. It's about information. When a quantum system becomes entangled with a measurement apparatus, even a simple one, the superposition collapses. Reality chooses a path. But even if no conscious mind is needed, the result is no less profound. It means that the properties of a system are not written in stone. They emerge through interaction, through relational measurement. The electron does not carry a predetermined path. It carries a cloud of options. Only when it interacts with the rest of the world does one of those options become real. In fact, the very idea of a fixed reality, independent of observation, begins to fray at the edges when considered in quantum terms. The universe may not be made of things, but of events, of outcomes born from interactions, relationships, and decisions made at the tiniest scales. You may wonder whether this applies only to isolated particles in labs, or if the principle has broader meaning. The answer lies in the subtlety of quantum decoherence, the process by which quantum systems lose their superposition when exposed to their environment. Decoherence doesn't destroy the wave function, it disperses it. The information still exists, but becomes entangled with so many other variables that the system effectively behaves classically. That's why we don't see tables flickering between states or cats existing in multiple positions. The interactions with the surrounding world collapse their uncertainty before we ever notice. But in the right conditions, low temperatures, isolation from noise, quantum effects scale, superpositions have been observed in carbon molecules, in superconducting circuits, and in carefully shielded ions. Reality's flexibility is not limited to the microscopic. It simply needs the right context to reveal itself. So what does it mean to live in a world where reality is defined by interaction? It means that the universe is less like a static sculpture and more like a story unfolding. It's not that nothing exists until it is seen, but rather that the final form of anything, the specific outcome, is only determined at the moment of measurement. The structure is probabilistic, not absolute. This might seem unsettling at first, but it carries with it a quiet reassurance that possibility is always present. That the world at its core is not rigid, but responsive. That new outcomes are always waiting to be realized. Reality, then, is not something imposed on you, it's something you participate in. Not by willing it into being, but simply by being part of the system. You are not a distant observer. You are entangled with the world, shaping its contours just by being within it. In this way, observation is not just a passive act, it is a form of connection, a moment when one part of the universe influences another, collapsing uncertainty into clarity. And every moment of awareness, of measurement, is a kind of gentle creation, one possibility chosen from many. So, when we say that reality doesn't exist until it's observed, we don't mean that the world is an illusion. We mean that the details, the specifics, the here and now, those are waiting to be defined, waiting for interaction, waiting for you. Chapter 6. You are a cloud of probabilities. It's tempting to think of yourself as a well-defined object, a coherent collection of cells, tissues, and memories contained within a distinct body. Classical physics supports this view. It treats matter as solid and predictable, your position in space as certain, your momentum as measurable. But the deeper you zoom in, past organs, past cells, past even atoms, into the realm of fundamental particles, this certainty dissolves. What you find is not a fixed entity, but a haze, a blur, a cloud of probabilities. At the quantum level, particles do not behave like marbles or miniature planets. They are described by wave functions, mathematical structures that define the likelihood of where a particle might be, or how fast it might be moving, or which energy level it might occupy. These wave functions are not approximations. They are the most accurate tools physicists have for predicting quantum behavior. But they do not give exact answers, only probabilities. This means that when you try to pinpoint the location of an electron, you don't get a single answer. You get a probability distribution, a map of where the electron is more or less likely to be found. It doesn't have a single well-defined position until it is measured. Before that moment, it exists in a spread-out state, a superposition of all the places it could be. Since you are made of electrons and protons and neutrons and quarks, this same uncertainty applies to you. Not at the scale of your entire body, of course. On the macroscopic level, quantum fuzziness averages out. But at your most fundamental level, you are not composed of rigid, tightly packed pieces. You are composed of fields of possibility, always in motion, always uncertain. When a physicist calculates the shape of a hydrogen atom, they don't draw sharp orbits. They draw fuzzy clouds, electron orbitals that show where the electron is likely to be found. These orbitals are not locations, they are likelihoods. The electron is not a point on a path, it is a probabilistic presence smeared around the nucleus. This is not a metaphor, it is how matter actually behaves. Particles exist as a set of potentialities, states that only become defined through interaction. Until then, they are suspended in a sort of quantum limbo, a cloud of maybe. And this, strange as it may sound, is what makes up you. Your particles are not located in one place or another with absolute certainty. They exist in ranges, bound by the rules of Heisenberg's uncertainty principle. The more precisely you know a particle's position, the less precisely you can know its momentum. And the more precisely you know its momentum, the fuzzier its location becomes. This isn't a flaw in measurement, it's a fundamental property of existence. So what does this mean for you? It means that your body, at its most elemental level, is not static or sharply defined. It is fuzzy, fluid, and unresolved until measured or interacted with. You are not a hard object. You are a fluctuating collection of possibilities, a cloud of quantum states constantly shifting in response to the environment. Even your brain, often thought of as a deterministic machine, is built on top of these probabilistic foundations. While most brain processes behave classically at large scales, individual molecular events, such as the tunneling of electrons or the precise folding of proteins, can exhibit quantum uncertainty. There are even hypotheses that certain aspects of consciousness or decision-making might involve quantum coherence, although these remain speculative. And yet, even without resorting to deep speculation, we can say with confidence the materials that compose your body are not solid in any absolute way. They vibrate, they shift. They do not exist in fixed positions, but in probability distributions. This view opens the door to a profound shift in how we understand identity. If the core components of your body exist in states of uncertainty, then what does it mean to say, "This is me"? Are you the location of your molecules? The pattern of their arrangement? The sum of their probabilities? You are not a fixed sculpture of atoms. You are more like a waveform, temporarily stable, yet fundamentally unresolved. That may sound unsettling, but it also means that you are not stuck, that at every moment you are a dynamic event, not a static object. You are being shaped and reshaped, not just biologically or emotionally, but physically, through the ceaseless unfolding of probabilities. And this dynamism is not chaotic. It is guided by laws, rigid, mathematical, and extraordinarily reliable. Quantum mechanics does not abandon structure. It simply reframes it. Instead of prescribing exact outcomes, it provides likelihoods, and remarkably, those likelihoods build the world with uncanny precision. The structure of DNA, the reliability of chemical reactions, the stability of stars, all emerge from these probabilistic rules. Even at rest, your body is in motion. Particles tunnel through potential barriers. Electrons jump between energy levels. Molecules rotate, stretch, and bend in accordance with quantum rules. You are a storm of possibility, given temporary form by the entanglements and constraints of the systems around you. This also means that the boundaries between you and the world are not as sharp as they seem. If you are a cloud of probabilities and so is everything else, then your particles are not separate from the particles around you. They overlap, they interact, they exchange momentum and energy, becoming entangled in subtle, continuous ways. You are not isolated. You are embedded in the probabilistic structure of the universe itself. And yet, from the shimmering fog of uncertainty emerges the familiar, the steady rhythm of breath, the shape of your hand, the sound of your voice. It is one of the great miracles of physics that such precise outcomes can arise from such uncertain beginnings. When you step back and view yourself not as a solid object, but as a cloud of probabilities guided by invisible laws, the notion of permanence begins to fade. What remains is process, a ceaseless unfolding of potential into form. Not randomness, but structured indeterminacy, the architecture of possibility. You are not static. You are not fixed. You are a momentary arrangement of uncertainties, resolved just enough to take shape in the world. And just as easily, those uncertainties continue onward, shifting, adapting, responding. In the end, to be a cloud of probabilities is not to be vague or unreal. It is to be deeply woven into the machinery of nature. It is to be in harmony with the most accurate descriptions of how the universe works. You are not outside the rules. You are their expression. And in a world where nothing is ever entirely certain, perhaps the most reassuring truth is this: uncertainty doesn't mean instability. It means flexibility, possibility, the chance, always for something new to emerge. You are, quite literally, potential made visible. Chapter 7. Electrons vanish and reappear constantly. In the classical world, objects persist. A chair stays in place until moved. A cup remains on the table unless acted upon. Persistence is the rule. But in the quantum world, the strange realm beneath the fabric of what we perceive, particles do not behave like miniature versions of everyday things. They don't simply sit still or move predictably through space. They blink, they shift, they vanish and reappear. Take the electron. For centuries, it was imagined as a tiny sphere orbiting an atomic nucleus, much like the Earth orbits the Sun. But this image, useful in its time, has long since been replaced. In modern physics, electrons are no longer thought of as discrete solid particles moving in defined paths. Instead, they are seen as excitations of a quantum field, disturbances in a background energy field that pervades all space. This means that electrons, like all particles, are not things in the traditional sense. They are events, temporary manifestations, fluctuations. They emerge into being, behave in ways governed by probability, and then fade back into the field from which they came. In a very literal way, electrons vanish and reappear constantly. This is not poetic abstraction. It is the direct result of our most successful physical theories, particularly quantum field theory, which underlies all of particle physics. According to this framework, what we perceive as empty space is anything but empty. It is alive with energy. Virtual particles constantly appear and disappear, borrowing energy from the vacuum and repaying it within timeframes so short they can't be directly measured. This flickering activity is not noise, it is structure. Even when you imagine a region of perfect vacuum, devoid of all matter, What's truly there is a foam of energy. In this vacuum, virtual electron-positron pairs are constantly forming and annihilating, existing for fractions of a second, too brief to be directly observed, but real enough to have measurable effects. The Casimir effect, for example, is a macroscopic demonstration of these vacuum fluctuations, where two uncharged metal plates experience a measurable force, pulling them together, caused by differences in vacuum energy between them. Electrons themselves participate in this flickering existence. Though more stable than virtual particles, even a real electron, such as one found in your body or in an atom, is not a solid object sitting in one spot. Instead, it exists as a cloud of probability, and its interactions with its environment cause it to temporarily disappear from one region and emerge in another. This isn't teleportation, it's quantum tunneling, a process by which particles move through barriers without ever physically passing over them. Quantum tunneling is one of the most dramatic demonstrations of this vanishing act. Imagine a ball sitting at the base of a hill. In classical mechanics, it must possess enough energy to roll over the hilltop to reach the other side. But in quantum mechanics, an electron doesn't need to climb the barrier. Its wave function extends beyond the wall, and sometimes, predictably, statistically, it simply appears on the other side. No trace, no climb. It wasn't there, and then it was. This isn't rare or exotic. Quantum tunneling is responsible for the nuclear fusion that powers the sun. Without it, protons in the sun's core would never overcome their mutual repulsion to fuse into helium. The temperature and pressure alone wouldn't be enough. It is only through tunneling, through this constant vanishing and reappearing, that stars shine. This behavior is baked into reality. When an electron is not being observed or measured, it does not have a specific location. It is not hiding somewhere, waiting to be found. It simply does not exist in the way we commonly think of objects existing. It exists only as a probability amplitude, a spread of likelihoods across space. And when we do interact with it, when we detect it or measure it, it localizes, appearing in a specific spot for a specific moment. Then, once again, it delocalizes. Its definite properties dissolve back into uncertainty. Its position smears across space. Its presence becomes probabilistic once more. This constant dance between presence and absence, between wave and particle, is not an aberration. It is what allows particles to interact, to bond, to move, to change. Importantly, the disappearance of an electron doesn't imply destruction. Nothing is being lost. Instead, what vanishes is our ability to define it precisely. The electron still exists within the quantum field, but it no longer has a well-defined location, momentum, or energy until it's forced to take one through interaction. Until then, it hovers in a realm of indefinite being, not gone, not present, but somewhere in between. This flickering behavior also helps explain phenomena like spontaneous emission, where electrons in excited states around atoms jump to lower energy levels and emit photons. The transition is not a smooth glide, but a sudden reconfiguration, a non-deterministic leap from one quantum state to another. One moment, the electron is in a higher orbital. The next, it is not. The photon it emits carries away the energy difference, but the electron's path was not tracked. It simply changed state. And what about inside the atoms of your own body? There, electrons don't orbit like planets. They occupy standing waves, regions of space where they are likely to be found. And yet, those regions are not static. The electrons move, shift, and tunnel through the atomic landscape. They never sit still. They never settle. They flicker through existence, bound only by the probabilistic structures of quantum mechanics. This gives rise to a startling realization. Even the matter that makes you up, your hands, your brain, your heart, is not composed of stable, enduring particles. It is composed of events. Electrons that briefly exist in one state and then flicker to another. Waves that become particles and then dissolve again. The continuity you feel in your body, in the world, is an illusion crafted by countless quantum events, resolving in patterns that remain consistent. In a strange way, this impermanence is what allows for permanence. The consistency of the quantum laws, the predictable statistics governing how often electrons tunnel, interact, or fluctuate, is what gives rise to stable matter. Your body may be built from particles that blink in and out of existence, but the rules behind those blinks are unchanging. The patterns they form persist. This dynamic nature isn't something to fear. It's what allows molecules to bond, cells to function, thoughts to arise. The quantum dance of electrons is not just weird, it's necessary. Without it, the universe would be static, motionless, dead. And so, even now, within you, electrons are vanishing and reappearing. Not once, not occasionally, but constantly. Every second, in every cell. A flicker here, a presence there, dissolving into field, re-emerging into space, entangling, scattering, resolving, then doing it all again. You are not composed of things, frozen and solid. You are composed of ripples, tiny bursts of temporary being that emerge from the deep fabric of the quantum world. You are built from vanishing points. And yet somehow, here you are, breathing, thinking, alive. Chapter 8. Entanglement connects you to the universe. In the everyday world, distance separates us. A person in another room, another city, or another galaxy is isolated by space. Communication takes time. Cause and effect follow linear paths. This makes sense in the classical view of the universe, where objects interact locally, one pushing or pulling on another through space. But in the quantum world, things are different. Sometimes, distance doesn't matter at all. This is the strange, verified reality of quantum entanglement. Entanglement occurs when two or more particles become linked in such a way that their quantum states are no longer independent. Instead, they form a single unified system, even if they are physically separated by light years. Measuring the state of one particle immediately affects the state of the other, regardless of the distance between them. This isn't just theory. It has been demonstrated again and again in laboratories. Pairs of photons can be generated such that they share a property, like polarization, in a correlated manner. Measure one photon, and its partner state is instantaneously determined. This correlation is stronger than anything classical physics can explain. Einstein famously called it spooky action at a distance, troubled by the idea that information could travel faster than light. But experiments show that no information is transmitted, at least not in a way that can be used to send messages or signals. The key is this: entangled particles are not separate in the way we imagine them. They don't carry pre-assigned values waiting to be revealed. Instead, their properties are undefined until measured, but the outcomes are linked. The entangled system must maintain consistency, even when its parts are far apart. It's as if reality itself bends to preserve harmony. To understand how profound this is, imagine two entangled particles set to opposite ends of the galaxy. If you measure one and find it up, the other must instantly be down. Not because a signal was sent, but because both particles are part of a shared state, one that stretches across space like an invisible thread. Their identities are not fully individual, they are relational. And entanglement is not fragile. It can persist through time, across distance, even in the face of environmental interference, at least under the right conditions. Quantum physicists have preserved entangled states over hundreds of kilometers on Earth, and even between ground stations and satellites in orbit. The phenomenon remains robust, consistent, and deeply puzzling. So what does this have to do with you? You are made of particles. Those particles have histories. They have been part of reactions, collisions, emissions. Many have interacted with other particles in entangling ways. some may still be part of extended quantum systems. You are, at a fundamental level, embedded in a vast network of correlations. And while most entanglement is lost quickly through a process called decoherence, the underlying fact remains: your existence is not strictly localized, it is connected. Entanglement reminds us that the universe is not made of isolated objects, but of relationships. That systems must be understood not only by examining their parts, but by understanding how those parts relate to others. In classical physics, the world is a collection of distinct entities. In quantum mechanics, the world is a tapestry of intertwined possibilities. This has practical consequences. In quantum computing, entanglement allows qubits to share information non-locally, enabling calculations far beyond the reach of classical machines. In quantum encryption, entanglement makes it possible to detect eavesdropping, because any measurement of an entangled system changes it. These technologies are not dreams, they are already in development, and they work because the universe at its root is non-local. But beyond the technology lies something more personal. Entanglement challenges the idea of separateness. It suggests that you are not cut off from the rest of the cosmos, but part of a larger structure, one where influence does not always depend on proximity, where connection is not limited to visible links. You are not a closed system. You are permeable to context. Your particles interact, entangle, and decohere with the environment constantly. You are shaped by fields, influenced by history, embedded in systems too complex to trace. But those systems are real. They are part of you. There is also something comforting in this picture. Entanglement tells us that connection is not always limited by space, that unity can persist even when things appear separate. In a universe so vast and often cold, that simple truth carries weight. At the scale of daily life, these effects may not be noticeable. We don't walk around experiencing quantum correlations, but that's because the world we move through is built on emergent classicality, a layer of order that arises from the averaging out of quantum possibilities. Yet the foundation remains strange, entangled, probabilistic, and even if we don't feel those entangled threads directly, their presence shapes the structure of reality. The stability of matter, the coherence of atoms, the flow of information, all rely on principles that include entanglement. Every interaction you've ever had, every photon that's bounced off your skin, every breath of air that's exchanged heat with your body, those are all quantum events, each with its own subtle correlations. Consider this: the light that enters your eyes and allows you to see is made of photons. Those photons may be entangled with others from their source, whether a distant star or a nearby screen. The electrons in your body repel those photons through electromagnetic interactions. The warmth you feel, the image you form, the signal your brain interprets, all arise from these encounters. You do not experience them as entanglement, but they emerge from it. Even memory, identity, and awareness rest on processes that rely on trillions of quantum interactions. Your neurons function classically on the surface, but they are built from quantum materials. Their order emerges from systems that once and perhaps still shared information non-locally. And so, entanglement isn't just a trick of physics or a footnote in textbooks. It is part of what makes reality coherent. It is the glue that holds quantum systems together across space. It is the reminder that the universe is more relational than mechanical. It may not allow faster than light communication. It may not let you send thoughts across the stars, but it tells you something subtle and strangely reassuring. The universe is built on connection, and you are part of that. You are not a fragment, floating alone. You are entangled with every breath, every photon, every moment of interaction. Somewhere, in ways you'll never fully measure, particles that once brushed against yours carry echoes of your existence. And the particles in your body carry the memory of encounters too, moments of shared state, however brief, that tie you to the greater web. You are more than the sum of your parts. You are the pattern of their relationships. And in that pattern, you are never entirely alone. Chapter 9. Quantum tunneling makes the impossible happen. In classical physics, barriers are absolute. A ball will not roll uphill on its own. A train cannot pass through a mountain without a tunnel. If something stands in your way, energy is required to overcome it. This is how the macroscopic world behaves. Obstacles demand effort. Every event has a cost, and actions are constrained by energy budgets. But the quantum world plays by different rules. At this scale, barriers are not necessarily impenetrable. Particles can cross them, not by climbing over, but by going through, even when they seemingly lack the energy to do so. This phenomenon is known as quantum tunneling, and is one of the most striking examples of how the microscopic world defies our everyday intuition. To visualize it, imagine a tiny particle like an electron approaching a barrier, a wall of potential energy. Classically, if the particle doesn't have enough energy to reach the top of the wall, it should stop and bounce back. But in the quantum realm, particles are not just localized points. They are described by wave functions, spread out probability distributions that ripple through space. These waves can extend into regions where the particle would not be allowed classically, and in some cases, a part of the wave continues on through the barrier, emerging on the other side. This means there is a non-zero chance of finding the particle where it shouldn't be. It hasn't climbed the wall. It hasn't punched a hole. It has tunneled through, a process allowed not by brute force, but by the mathematics of quantum behavior. This isn't some abstract possibility. Quantum tunneling happens constantly in the physical world. In fact, without it, stars wouldn't shine. Inside the sun, extreme temperatures and pressures push hydrogen nuclei together in a process called nuclear fusion, which releases the energy that warms our planet and powers life. But protons, the positively charged nuclei of hydrogen atoms, repel each other with tremendous force. Classical physics says they should never get close enough to fuse. The energy in the sun's core, while immense, is not enough to overcome this repulsion entirely. And yet, fusion happens because of quantum tunneling. The protons don't have to overcome the barrier. They can tunnel through it. Even though the chance of this happening for any individual pair is small, the sheer number of particles and collisions makes the process statistically reliable. Tunneling is what makes the sun burn. It also drives processes much closer to home. One example is alpha decay, a type of radioactive decay in which an unstable nucleus emits a cluster of particles, 2 protons and 2 neutrons, called an alpha particle. According to classical models, these alpha particles should be trapped inside the nucleus by a strong nuclear potential. But again, they manage to escape. They tunnel through the barrier, emerging from the nucleus, despite having insufficient energy to do so directly. This process is predictable. We can measure the decay rates of radioactive isotopes, precisely because tunneling obeys well understood statistical laws. It's not random in the chaotic sense. It's random in the quantum sense, where probabilities can be calculated with great accuracy, even if individual events remain unpredictable. Quantum tunneling isn't just a curiosity of nature, it's also something we harness. Scanning tunneling microscopes, instruments capable of imaging individual atoms, rely on this effect. When a conductive tip is brought extremely close to a surface, within a few angstroms, electrons can tunnel across the gap, even though there is no physical contact. The resulting current is sensitive to the distance between the tip and the surface, allowing researchers to build up high-resolution images of atomic landscapes. In modern electronics, tunneling is both a feature and a challenge. As transistors in computer chips shrink to nanometer scales, electrons can begin to tunnel through thin, insulating barriers. Sometimes intentionally, sometimes not. This places fundamental limits on how small traditional electronics can become, and it also opens doors to quantum computing, where tunneling can be used to manipulate qubits and perform computations far beyond the capabilities of classical machines. But beyond the applications and the math lies something quietly profound. Tunneling reveals that the universe does not always follow the paths we expect, that what seems impossible, impenetrable, may not be if you look closely enough. It suggests that the universe is less rigid than it appears, that nature allows for exceptions in the most extraordinary ways. At its heart, tunneling is a testament to the probabilistic nature of reality. In the classical world, if you don't have enough energy to get over a hill, you simply can't go. But in the quantum world, you might, occasionally, unpredictably, just end up on the other side. No effort required, no direct cause, just a non-zero chance written into the mathematics of being. This idea challenges how we think about obstacles and boundaries, not just in physics, but metaphorically. If a particle can appear on the other side of a barrier it has no business crossing, then perhaps the notion of what's possible needs to be reevaluated. Not everything is deterministic. Not everything is blocked forever. Some paths may open not through force, but through probability. And the rules that allow for this are not arbitrary. They are strict, precise, and universal. Tunneling is not chaos, it's law. It happens because the wave functions describing particles can extend beyond visible limits, because uncertainty allows for temporary violations of classical constraints, as long as conservation laws are respected over time. These impossibilities are baked into reality. What's most remarkable is that tunneling is not rare. It's happening inside your body right now, in biochemical processes, in enzyme reactions, in the transport of electrons across membranes. Quantum tunneling plays a quiet, essential role. It doesn't announce itself, but it's there, allowing processes to proceed more efficiently even when classical models would say they shouldn't. So much of what we take for granted, sunlight, radioactivity, even cellular respiration, depends on this gentle defiance of classical limits. Tunneling is not about breaking the rules. It's about understanding that the rules are broader than we once imagined. If you think of reality as a series of walls, quantum tunneling reminds you that some of those walls are more like curtains, barriers that can be passed through, not by brute force, but by existing in a world that allows for soft edges, a world where possibility is never fully zero, where the improbable is simply part of the landscape. And in this landscape, what seems impossible can happen, not often, not easily, but often enough to shape the stars. Chapter 10. Even empty space is teeming with activity. When we think of emptiness, we imagine stillness, a room without people, a vacuum without air, a void without substance. In classical thinking, empty space is the absence of matter, a blank backdrop against which the real action of the universe plays out. But quantum physics paints a very different picture. In the quantum world, there is no such thing as true emptiness. Even space that appears completely void of matter and energy is far from inactive. Beneath the surface of apparent nothingness, space itself is seething with invisible motion, a restless dance of fields, fluctuations, and temporary particles appearing and vanishing in the blink of a moment. This strange phenomenon is known as vacuum fluctuation. According to quantum field theory, even the most perfect vacuum is not truly empty. It is filled with fields, quantum fields that stretch throughout the universe. These fields are not static. They are constantly shifting, oscillating, and interacting. And as they do, they give rise to temporary disturbances, virtual particles that pop into and out of existence. These particles are called virtual because they cannot be directly observed in isolation. They are not detected like real particles in particle accelerators. Instead, they are inferred from the effects they leave behind, slight shifts in energy levels, subtle forces between particles, and even the structure of space-time itself. Virtual particles exist for just long enough to borrow energy from the vacuum and then disappear, returning that energy before any rule is broken. This might sound like science fiction, but it's supported by measurable consequences. One such consequence is the Casimir effect, a phenomenon where two uncharged metal plates placed very close together in a vacuum are drawn toward each other. No classical force explains this. Instead, it arises from differences in vacuum energy on either side of the plates. The quantum fields between the plates are restricted, reducing the density of fluctuations there. The imbalance creates a pressure that pushes them together. And then there's the Lamm shift, a tiny change in the energy levels of hydrogen atoms caused by interactions with virtual particles in the vacuum. These shifts were measured with extraordinary precision and matched the predictions of quantum electrodynamics, the theory that governs how light and matter interact. The match is so precise that it remains one of the most successful predictions in the history of physics. What these results show is that space is not passive. It is not a container. It is an active participant in the structure of reality. Even when there are no particles, no fields you can measure, no light, no matter, there is still activity. Zero-point energy, the lowest possible energy state of a quantum system, is never truly zero. There is always a residual buzz. This idea has far-reaching implications. In quantum mechanics, the vacuum is not a neutral background. It affects everything. It can influence the behavior of atoms, change the decay rates of particles, and even determine the structure of forces. More dramatically, physicists believe that vacuum energy may be tied to one of the deepest mysteries in cosmology, the accelerated expansion of the universe. Observations of distant galaxies show that the universe is not just expanding, it's speeding up. This acceleration is attributed to a mysterious component known as dark energy. One hypothesis is that this dark energy is related to vacuum energy, the latent, irreducible energy present even in empty space. If this is true, then the fate of the cosmos is being shaped by the invisible hum of quantum fields. The future of stars, galaxies, and perhaps even time itself may hinge on the fluctuations of empty space. There is something quietly profound about this. We are taught to look for meaning in matter, in the planets, in the stars, in the bodies we inhabit. But quantum physics reminds us that the spaces between things are just as vital, that what appears to be nothing may in fact be everything. Even the stability of atoms depends on the vacuum. Electrons orbit nuclei in discrete energy levels, and transitions between these levels are influenced by interactions with the quantum vacuum. Virtual particles can momentarily shift an electron's position or energy, even changing the likelihood of certain atomic processes. These effects are tiny, but they accumulate. They shape the chemistry of the universe. At a more speculative level, some theories of physics suggest that all of reality may have emerged from a vacuum fluctuation. In models of cosmic inflation, the early universe began as a quantum field fluctuation that rapidly expanded into the space-time we now observe. In this view, even existence itself could have begun from a state that looked, from the outside, like nothing. But that nothing was never empty. If you could zoom in on a cubic centimeter of vacuum, deep in intergalactic space, far from any stars or galaxies, you might expect to find silence, stillness. Yet the quantum view tells us that this cube would be bustling with activity. Particles popping into existence and annihilating, fields vibrating, energy briefly borrowed and repaid. A theater with no audience, but no less a performance. And this activity is not meaningless. It has structure. It follows rules. It contributes to the properties of particles, the dynamics of the cosmos, and the passage of time. In a universe where all things seem to arise from interaction, even the vacuum is a partner. So what does this mean for you? It means that silence is never total. That even in the most isolated moments, alone in a quiet room, in the stillness before sleep, the universe is busy, just beneath the surface. The same space between your fingers, the same gaps between molecules in your body are filled with invisible motion. And in some way, this activity is what makes you possible. Without vacuum fluctuations, atoms would behave differently. Forces would not balance in the same way. Light might not behave as it does. The world, as you know it, would be unrecognizable or not exist at all. Even the light you see, the warmth you feel, the radiation of stars, these are all shaped by how particles interact with the vacuum. In every corner of your experience, there is a quiet presence, the churning of empty space. We are used to thinking of space as the absence of content. But in physics, content is everywhere. Even where there is nothing, there is energy. Even where there is no motion, there is fluctuation. Stillness is only apparent. So the next time you imagine emptiness, try instead to imagine potential. Fields waiting to ripple, particles waiting to form, patterns waiting to emerge. Even nothingness is full of something, and that something is the foundation of it all. Chapter 11. Time is not what you think. Time feels familiar. We live by it, measure it, chase it. Seconds tick by with comforting regularity. Clocks spin. Days pass. Cause leads to effect. It seems obvious that time flows forward, like a river, carrying us from past to future. But the deeper we look into physics, the stranger time becomes. Beneath its everyday surface, time may not be what we think it is. In classical mechanics, time is absolute. It flows at a constant rate, the same for everyone, everywhere. Newton treated time as a background parameter, a container in which events unfold. But this view began to shift with Einstein's theory of relativity, which showed that time is not a universal constant. It is elastic. It bends. In special relativity, time slows down for objects in motion relative to others. A fast-moving spaceship ages more slowly than a stationary observer. In general relativity, gravity stretches time too. Clocks tick more slowly in strong gravitational fields. This is not just theory, it has been measured. Atomic clocks on airplanes run at slightly different rates than those on Earth. GPS systems account for these relativistic effects constantly, or they would lose accuracy within hours. So time is not fixed. It is relative. It is shaped by motion and mass. And this alone is enough to unseat our intuitive understanding. But quantum physics adds another layer of mystery. At the quantum level, time behaves differently depending on how it's treated in the mathematics. In the Schrödinger equation, which governs the evolution of quantum systems, time appears as an external parameter, unchanging, classical. But the particles it governs are probabilistic. They exist in superpositions. They evolve over time, but not along a single, well-defined path from one moment to the next. This mismatch between the classical treatment of time and the probabilistic nature of particles raises deep questions. If everything in the universe is ultimately quantum, why should time remain classical? Why should it flow in a single direction at all? Some physicists propose that time is not fundamental. Instead, it may be emergent, a property that arises from deeper quantum relationships. Just as temperature emerges from the collective motion of atoms, time may arise from patterns of entanglement, entropy, or correlations among particles. One compelling clue comes from thermodynamics, the branch of physics dealing with heat and disorder. The second law of thermodynamics states that in a closed system, entropy, the measure of disorder, tends to increase. This law gives time its familiar direction. Eggs break, ice melts, structures decay. We remember the past but not the future because entropy increases in one direction. But entropy is a statistical phenomenon. The fundamental laws of physics, Newton's equations, Schrödinger's equation, even Einstein's general relativity, are time-symmetric. That is, they work the same whether time runs forward or backward. Nothing in the equations requires that time have a direction. And yet, in practice, we experience only one. Why? Some theorists believe that the arrow of time is tied to the initial conditions of the universe. At the Big Bang, the cosmos was in an extremely low entropy state. From there, entropy increased, giving rise to the one-way flow we call time. In this view, time is a consequence of how the universe started, not of any deep rule about its mechanics. Others look to quantum entanglement for answers. In highly entangled systems, correlations between particles can create a sense of direction, a kind of informational asymmetry that gives rise to a temporal order. According to some models, time itself may emerge from the flow of information between entangled subsystems. And then there is the notion of the block universe, a view from relativity that treats past, present, and future as equally real. In this model, time does not flow. All events, past and future, exist together in a four-dimensional structure. The sense of movement, of change, is not a property of the universe, but a feature of consciousness. You are not riding a river. You are a line in space-time, extended from birth to death. Every moment, already there. This view is difficult to accept. It clashes with experience. We feel time. We age. We make choices. But in the block universe, all moments are equally real. There is no now, only a sequence of events experienced subjectively. Other approaches go even further. In some formulations of quantum gravity, attempts to unite quantum mechanics and general relativity, time disappears entirely. The equations describing the universe do not include time as a variable. What emerges instead are relations between configurations, how one state of the universe is related to another. The sense of duration is reconstructed from correlations. This doesn't mean time is an illusion, but it might mean that time is not a thing, but a process, something constructed by observers from interactions, from memory, from entropy. Something built, not given. Your own experience supports this. Time doesn't feel the same every day. Moments stretch or collapse depending on your focus, your state of mind. A single hour can feel eternal or vanish in a breath. This isn't just psychology. It reflects the brain's interpretation of events, built from sequences, rhythms, and predictions. Time, to us, is not just what the clock measures. It is what we notice changing. And in the quantum world, change does not always happen continuously. It can occur in jumps, discrete transitions between energy levels, quantum leaps that defy the smooth flow of classical time. A particle may exist in one state, then another, with no clear in-between. This discreteness adds another wrinkle to the idea of time as a smooth line. So what then is time? Perhaps it's not a river, but a scaffolding we build to make sense of motion. Perhaps it's not a substance that flows, but a pattern that emerges. Perhaps it's not a property of the universe, but a language we use to tell the story of change. This doesn't make time less real. It makes it more fascinating, because it suggests that your experience of time, your memories, your anticipation, your aging, is not merely a byproduct of an external clock, but part of the universe's way of organizing complexity. Time may not be ticking outside you. It may be something arising within you. And even if time is emergent, it still binds the universe together. It allows stars to evolve. It enables cause to precede effect. It gives shape to possibility. Without time, or something like it, events would have no structure. History would have no thread. Yet, the next time you look at a clock, consider what it doesn't show. It doesn't show the relativity of motion, the influence of gravity, the entanglement of particles, or the slow unfolding of entropy. It doesn't show that every second is a negotiated outcome between matter and geometry. It doesn't show the quantum processes underlying every tick. Time is not what you think. It is not simple. It is not fixed. But in its mystery, it offers something beautiful. A reminder that even the most familiar things, seconds, minutes, days, are deeper than they seem. Chapter 12. Energy can appear from nowhere. Briefly, energy is one of the most fundamental concepts in physics. It powers stars, fuels life, drives machines. We're taught that energy cannot be created or destroyed, only transformed, a principle known as the conservation of energy. It's a bedrock of classical physics and one of the most reliable rules in nature. But in the quantum world, things are not always so strict. At the smallest scales, energy can briefly appear where there was none before, emerging from the vacuum, existing for an instant, and then vanishing again. This isn't poetic metaphor. This is physics, and it's made possible by one of the most surprising principles in quantum mechanics, the energy-time uncertainty principle. This principle is a close relative of Heisenberg's uncertainty relation between position and momentum. It says that the more precisely we define the energy of a system, the less precisely we can define how long that energy lasts, and vice versa. And the consequences are profound. For extremely short periods of time, the conservation of energy becomes a little more flexible. What does that mean? It means that if you look at a small enough region of space over a short enough time, particles can briefly exist that shouldn't be allowed by classical rules. These are called virtual particles, not imaginary, but not directly observable either. They are fluctuations in quantum fields that borrow energy from the vacuum, live for a fleeting moment, and then disappear, repaying their energy debt before they can be noticed in any direct way. These particles don't show up in detectors. You can't isolate one, but their effects are real. They influence how real particles interact. They leave fingerprints. One famous example is the Lamb shift, a slight difference in the energy levels of electrons in a hydrogen atom caused by virtual particles flickering in and out of existence around the atom. It's tiny but measurable, and it precisely matches the predictions made by including vacuum fluctuations in the equations. Another example is the Casimir effect. Place two uncharged metal plates close together in a vacuum, and they'll attract each other. There's no classical explanation for this. The effect arises from the difference in vacuum energy between the inside and outside of the plates. Fewer fluctuations can exist in the narrow space between them, creating a pressure imbalance. The plates are pushed together, not by any real particle, but by the restless sea of quantum nothingness. Even the force that binds protons and neutrons inside atomic nuclei, the strong nuclear force, gets corrections from these fleeting energy events. Quantum field theory includes endless terms involving virtual particles, each popping into and out of existence, contributing just a little to the behavior of the world. And yet, when you add them all up, you get one of the most accurate models ever constructed. Quantum electrodynamics, which governs how light and matter interact, makes predictions that match experiment to more than 1/1,000,000,000%. So, despite being transient and indirect, these fluctuations shape everything. They determine the structure of atoms. They shift the spectrum of starlight. They alter the way forces behave. In the quantum view, what looks like empty space is alive with invisible motion. This baseline activity is sometimes referred to as zero-point energy, the minimum amount of energy a quantum system can have, even at absolute zero temperature. Unlike in classical physics where a system at zero temperature would be perfectly still, a quantum system always retains a residual motion. Its particles vibrate, its fields shimmer. This might seem like an abstract curiosity, but it could have cosmic consequences. Some physicists believe that zero-point energy might contribute to the mysterious phenomenon of dark energy, which appears to be accelerating the expansion of the universe. The vacuum energy of space itself might possess enough latent pressure to shape the future of everything, though the numbers don't quite line up yet. The calculated energy density of the vacuum is vastly higher than what we observe cosmologically. This vacuum catastrophe remains one of the great unsolved puzzles in theoretical physics. Still, the idea is tantalizing, that space itself contains an energy reservoir, always full, never still. That from this foundation, all things rise. Some physicists even speculate that our universe could have begun from such a fluctuation, an uncaused emergence from a high-energy vacuum. In quantum cosmology, tiny fluctuations in a vacuum-like field could have expanded rapidly in a burst of cosmic inflation, giving birth to the universe we know. In this picture, the Big Bang wasn't the beginning of time from absolute nothingness, but a transformation of energy from a deeply unstable quantum vacuum into space, time, matter, and radiation. And it all starts with energy appearing from nowhere, briefly, but enough. What's especially strange is how these ideas shift our understanding of nothingness. We often imagine nothing as the absence of everything, a blank slate. But in the quantum world, nothingness is an illusion. The vacuum is not empty, it is structured, it is defined by the fields that permeate the universe. Even when no particles are present, the fields remain. They fluctuate. They respond. They are the stage, the actors, and the script, written in waves of probability. In experiments, this fluctuation-driven behavior is not just conceptual. Physicists use Feynman diagrams, visual representations of particle interactions, to calculate probabilities of outcomes in collisions and decays. These diagrams include loops and internal lines representing virtual particles, contributions from energy that appears, acts, and disappears before it can be directly observed. Without these, the predictions would be incomplete. It is this invisible choreography that makes the visible world work. All of this leads to a quiet realization that energy, which seems so concrete, is more subtle than we thought. That the rules we trust in daily life, the conservation laws that keep engines running and planets orbiting, are not absolute at all scales. They are statistical truths emerging from deeper layers of reality that are more flexible, more forgiving. At the quantum level, certainty dissolves, and with it, so does the notion of permanence. Energy becomes something that can be borrowed and returned, that can flicker and fade, that can show up for a moment, leave a trace, and vanish, never quite violating the rules, but never fully obeying our expectations either. This is not chaos. It's structure. It's a different kind of order, one where fluctuations are allowed as long as they are brief, where impossibilities are permitted in microdoses, where rules are not broken, but bent just enough to let the universe remain alive. You may never foil this happening. You may sit in silence and think the world is still. But beneath the stillness, the vacuum hums, and in that hum, energy flickers, briefly, brilliantly, beautifully, and it is enough to hold the stars in place. Chapter 13, Particles Can Behave Like Waves. If you look at the world around you, it seems obvious that objects are distinct. A pebble is a pebble. A beam of light is something else entirely. We classify things as particles or waves, solid or fluid, definite or diffuse. But the quantum world refuses to follow these boundaries. In fact, it undermines the categories themselves. One of the most surprising principles of quantum mechanics is this: particles can behave like waves, and waves, like those of light, can act like particles. This is not an approximation. It's a deep, irreducible truth about the fabric of reality. The first clues came from light itself. In the 19th century, experiments showed that light behaved like a wave. It could interfere, diffract, and refract, spreading out, bending around edges, and forming patterns of alternating brightness and darkness. But then came the photoelectric effect, where light striking a metal surface knocked loose electrons in a way that only made sense if light arrived in discrete, quantized packets, photons. Einstein's explanation of this effect in 1905 proposed that light had a dual nature. It behaved like a wave in some experiments, like a particle in others. This revolutionized physics and earned him the Nobel Prize. But it raised an even deeper question. Could matter too possess this dual identity? In 1924, physicist Louis de Broglie proposed something radical, that all particles of matter, not just photons, also have an associated wavelength. The smaller and lighter the particle, the longer the wave. This was not a metaphor. He was suggesting that electrons, protons, and even entire atoms could exhibit wave-like behavior under the right conditions. Then came the proof. In 1927, Clinton Davison and Lester Germer performed an experiment in which electrons were fired at a crystal surface. Rather than behaving like tiny bullets, the electrons produced an interference pattern, a hallmark of wave behavior. Their experiment was later confirmed by George Thomson, showing that electrons could indeed diffract just like light. These results validated de Broglie's hypothesis and gave birth to a cornerstone of quantum mechanics, wave-particle duality. This means that electrons don't travel through space as tiny, well-defined points. Instead, they exist as wave functions, mathematical descriptions that represent a spread of probabilities. These waves can interfere, overlap, and diffract. And only when a measurement is made, when you detect the particle's location, does the wave collapse into a single point. But until that moment, the electron is not in one place. It is in many places, or rather, it might be in many places. Its existence is a superposition of possibilities, and this is not limited to electrons. Protons, neutrons, atoms, even molecules made of dozens or hundreds of atoms, all of them have been shown to exhibit wave-like interference patterns in the lab. In 1999, physicists performed an interference experiment using molecules of C60 fullerene, a soccer ball-shaped molecule made of 60 carbon atoms. Despite their size, these molecules displayed wave behavior, forming interference patterns just like light. This means that the boundary between the quantum and classical world is not a clean line. It is fuzzy, gradual, scale-dependent. Everything in principle has a wavelength. For everyday objects like humans or baseballs, this wavelength is so small that quantum effects are impossible to notice. But the wave nature doesn't disappear. It just becomes immeasurably tiny. So what does it mean that a particle behaves like a wave? It means it can interfere with itself. Consider the famous double-slit experiment. If you fire photons or electrons or atoms at a barrier with two narrow openings and a detection screen on the other side, something remarkable happens. If you send them through one at a time, one after another, they eventually form an interference pattern on the screen. The particles seem to be interfering with themselves, as if each one somehow passed through both slits at once. And if you try to measure which slit the particle went through, the interference disappears. The pattern on the screen changes. Observation collapses the wave function and forces the system into a definite state. The very act of watching changes the outcome. This is not a trick. It is not due to experimental flaws. It is a built-in feature of reality, and it tells us something fundamental. The nature of matter is inseparable from the way we observe it. This wave-particle duality forces us to rethink what we mean by thingness. Is a particle a point, a wave, something else entirely? In quantum mechanics, a particle is not a static object. It is a manifestation of a field, shaped by boundary conditions and constrained by probabilities. It has both position and momentum, but not in absolute terms. The more precisely one is known, the less precisely the other can be. These wave properties are not just quirks, they are essential to the universe. They are what allow electrons to form orbitals around atomic nuclei, rather than spiraling inward and collapsing. They are what give atoms their size and structure. They are why chemistry works. Without the wave nature of particles, there would be no periodic table. No stable matter, no biological molecules. The interference of probability waves gives rise to the richness of form and function that we see everywhere in nature. And yet this wave nature also opens the door to entanglement, superposition, and the entire strange landscape of quantum behavior. It's what allows a particle to exist in multiple paths simultaneously, to interfere with possibilities, to act as if it knows all the ways it could behave, and then select one. From this perspective, a particle is not a thing moving along a path. It is a network of options, a ripple of probability whose fate is undecided until measured. The universe, at this level, does not deal in certainties. It deals in waves of potential. And as strange as this may sound, the mathematics works. The predictions match experiments with uncanny accuracy, from the shapes of molecules to the operation of semiconductors, from electron microscopes to lasers. The wave behavior of particles underpins much of modern technology, but beyond its utility lies a quiet philosophical shift. It tells us that identity is not binary, that something can be both and neither, that a particle does not have to choose until forced, and that the world at its most basic level is not made of things, but of tendencies, of interactions, of shapes and probability space. A particle behaving like a wave does not mean that reality is confused. It means that reality is richer than our labels, that form and substance are more fluid than they appear, that being is not confined to a point, but spread across possibility. You are made of particles, and every one of them, if isolated, could form a wave, could bend around an obstacle, could interfere, could exist in more than one place until forced to decide. You are a composition of certainties and uncertainties, a gathering of collapsed probabilities, and beneath all the structure and form, you are built from waves, waves that chose to become you. Chapter 14. Reality is made of fields, not things. In everyday life, we experience the world as a collection of things, objects with edges and names, a coffee mug, a cloud, a cat curled up in the sun. These things feel solid, distinct, and comfortably knowable. But if you peel back the layers, past the molecules, past the atoms, past even the particles that seem to form the building blocks of matter, you arrive at a very different picture, a picture not of things, but of fields. In modern physics, particles are not the most fundamental entities. They are not little balls of matter flying through space. Instead, every particle is an excitation, a ripple in a deeper, invisible field. There is an electron field, a photon field, a quark field. These fields stretch through all of space, even the vacuum. They are always present, always humming, even where no particles are observed. When we detect an electron, we're seeing a ripple in the electron field. When a photon hits your eye, it's a ripple in the electromagnetic field. What we call particles are simply the smallest possible vibrations in these invisible, ever-present structures. This is the framework of quantum field theory, the most accurate and successful description of nature yet devised. It unites quantum mechanics with special relativity, and it has withstood every experimental test thrown at it. According to this view, the entire universe is built not from particles, but from fields that interact, combine, and resonate with one another. Particles emerge only as brief, localized spikes in the ocean of these fields. And remarkably, every field has quantum properties. It can fluctuate, it can interfere, it can become entangled. The vacuum, which might seem like the absence of everything, is actually full of these subtle field interactions. Even empty, space is never truly empty. To understand just how far this idea goes, consider that every type of fundamental particle we know, electrons, photons, neutrinos, quarks, is simply a different kind of field vibration. The difference between them is not a difference in substance, but in the way the field vibrates. like the strings on a violin, where each note is produced by the same material vibrating at a different frequency. Particles are musical notes played by the underlying fabric of reality. In this sense, you are not made of particles. You are made of vibrating fields, wave-like excitations that give rise to form, structure, and behavior. The boundary of your body is not a line between you and not you, but a region where field excitations are particularly dense and complex. Your sense of solidity is not because the fields are solid, but because the rules of their interaction create the experience of solidity. And these fields are not static. They ripple and flex with energy. They can become distorted, curved, or compressed. They respond to temperature, to forces, to other fields. When two particles collide, what's really happening is that two field excitations interact, modifying each other's structure, exchanging energy, and perhaps creating new excitations in other fields. Even forces themselves, gravity, electromagnetism, the strong and weak nuclear interactions, can be understood as the effect of fields interacting with one another. The photon, for instance, is the quantum carrier of the electromagnetic field. The gluon mediates the strong force. The W and Z bosons mediate the weak force. In each case, these aren't things in the classical sense. They're packets of field energy, temporary deformations in a deeper continuum. This view also explains some of the more baffling features of the quantum world. Virtual particles, for instance, are field excitations that briefly emerge in the vacuum and vanish again before they can be directly observed. Their influence is felt in forces between particles, in shifts of energy levels, and even in the structure of space-time itself. The concept of particles as things falls apart when viewed too closely. An electron isn't a tiny sphere flying through space. It has no size in the classical sense. What it has is a wave function, a mathematical representation of how the electron's field is vibrating at any given point. The location of the electron is just where its field amplitude is highest. And even that is probabilistic. But this isn't just abstraction. The consequences of thinking in terms of fields are everywhere. The Higgs field, for instance, is what gives mass to other particles. Without it, electrons and quarks would be massless, and atoms couldn't form. The field permeates all of space, and particles interacting with it gain mass like a swimmer moving through molasses. The discovery of the Higgs boson in 2012 confirmed that this invisible field, one that fills the entire universe, really exists. It is difficult to overstate the shift this brings. We no longer live in a world of objects flying through a neutral void. We live in a medium, a sea of overlapping fields, each influencing the other, each defining what is possible. The universe is not an empty stage, but a vibrating network where every interaction is a chord, every movement a shift in frequency. Even space and time, in advanced theories of quantum gravity, may themselves arise from something deeper, emergent features of more fundamental fields that don't yet fit neatly into our models. The difference between space and field may one day dissolve entirely, and you, moving through this universe, are not separate from these fields. You are not riding on top of them. You are them, your body, your thoughts, your memories. They are patterns in field behavior, constrained by laws, sculpted by experience, and bound together by interactions that stretch across time and space. It's not that you are made of invisible stuff. It's that the pattern of interactions, the ripple of excitations, is what constitutes you. You are not a thing in a field. You are a localized expression of the field itself. And that's a powerful shift in perspective, because it means that solidity is not substance. It's structure. Identity is not a boundary, it's coherence. Being is not the occupation of space, but the resonance of fields in time. What we see as objects are simply the densest, most stable arrangements of field excitations. A rock is a compact cluster of vibrations. A A tree is a slower, evolving pattern. A star is a thermonuclear oscillation echoing through space. You are a self-organizing region of resonance held together by feedback loops, chemistry, and conscious awareness. And even in death, the fields remain. They do not vanish. They shift. They redistribute. The excitations change form, but the underlying structure of the universe continues. Nothing is ever truly lost. It just changes tone. So the next time you touch your hand to a wall, or gaze at a leaf fluttering in the wind, or speak a word into the air, remember, you're not interacting with things. You're engaging with fields, ripples in a seamless whole. And every interaction is a kind of music, composed by the laws of nature, played out in infinite variations across the stage of existence. You are not an object in the universe. You are the universe, momentarily resonating in your particular form. Chapter 15. The more you know about one thing, the less you know about another. Knowledge feels like accumulation. You gather facts, sharpen measurements, reduce uncertainty. The clearer your data, the more precise your understanding, or so it seems. But in the quantum world, precision comes at a cost. You cannot know everything at once. The more you pin down one property, the more another slips out of reach. This is not a flaw in our instruments. It's not a temporary gap in understanding. It is a built-in feature of the universe, formalized in one of the most important and counterintuitive principles of quantum mechanics, the uncertainty principle. First introduced by Werner Heisenberg in 1927, the uncertainty principle states that certain pairs of physical properties are inherently linked in such a way that the more precisely you know one, the less precisely you can know the other. The most famous of these pairs is position and momentum. If you try to determine exactly where a particle is, you lose information about how fast it's moving or in what direction. If you measure its momentum with perfect accuracy, its location becomes indeterminate. This isn't just a statement about practical limits. It's not that we lack the technology to measure both. Rather, it's a deep consequence of how nature itself behaves. At the heart of this phenomenon is the wave function, the mathematical entity used in quantum mechanics to describe particles. Particles aren't pinpoints with definite traits. Instead, they are described by wave-like distributions, spread out across space. A sharply peaked wave function in space corresponds to high uncertainty in momentum. A clean, narrow wave function in momentum space spreads widely across position. The more you can find the wave in one domain, the more it spills in the other. It's not unlike how a musical note becomes less precisely pitched the shorter it lasts. To get a pure tone, you need a long-duration wave. To get a sharp spike, you need many different frequencies. The same kind of trade-off appears in quantum physics. This relation isn't confined to just position and momentum. Other pairs of variables are conjugate, meaning they obey a similar uncertainty principle. One of the most important is energy and time. The more precisely you know the energy of a quantum system, the less precisely you can know how long it remains in that state. This is one of the reasons quantum fluctuations can occur. For very short durations, the conservation of energy can be temporarily violated within the limits set by this principle. It's what allows virtual particles to momentarily spring into existence and vanish again, briefly borrowing energy from the vacuum before repaying it within the allotted quantum grace period. These are not vague philosophical statements. They are precise, testable, and repeatable. Every quantum experiment bears their signature. They show up in electron microscopes, atomic clocks, and the behavior of light itself. Even technologies like MRI machines are indirectly shaped by the limits set by quantum uncertainty. But beyond the technical, the uncertainty principle invites us to rethink the very nature of information. In the classical world, we are used to the idea that a system can be known completely. If you know the position and velocity of every atom in a box, You can, in principle, predict its future and reconstruct its past. This is determinism. The universe in that view is like a vast clockwork, complex but predictable. Quantum mechanics changed that. Uncertainty is not a bug. It's not noise. It's a fundamental truth. At the smallest scales, the universe is indeterminate, not because we lack knowledge, but because the system itself does not contain fully determined values until they are measured. And even then, the act of measurement changes the system. The wave function collapses, and the probabilities resolve into a single outcome. But that outcome comes at the cost of losing information about its complementary property. You cannot keep everything in focus at once. This means that reality at the quantum level is not about absolutes. It's about relationships. What you can know depends on how you look. What you choose to measure determines what remains hidden. This may sound deeply unsettling. After all, we like to think of the world as concrete and knowable. But in another sense, this uncertainty is what gives rise to richness, to variety, to possibility. If everything could be known precisely and simultaneously, there would be no room for quantum tunneling, no entanglement, no probabilistic evolution of systems. The same strange effects that make quantum mechanics difficult to grasp are the very ones that make atoms stable, matter complex, and chemistry possible. Even your own body reflects this uncertainty. The electrons in your atoms are not neatly circling like planets. They exist in clouds of probability, described by orbitals that blur across space. Their exact positions and velocities are unknowable, but together they create the structure of the periodic table, of molecules, of life. There is something deeply human in this too. The more you focus on one thing, the more you lose sight of the rest. The more you specialize in a field, the more other domains become opaque. The sharper your vision in one area, the more limited it becomes elsewhere. And yet, this narrowing is not failure. It is how knowledge works, by trade-offs, by choices, by selective attention. The universe behaves in a similar way. It is not trying to hide things from us. It is showing us that perfect knowledge of everything is not possible, even in principle. And in doing so, it is reminding us that reality is not a list of facts, but a tapestry of potential. There is another way to interpret this principle, as a guide to how nature balances itself. No system can give up all its secrets. There must always be room for unpredictability, for motion, for evolution. And in that space, life emerges. Stars ignite, thought unfolds. You might think of uncertainty as a kind of privacy encoded into the universe, a protective blur that preserves the dynamic quality of existence. Nothing is frozen. Everything is in motion. And that motion comes with limits on what can be simultaneously known. This principle doesn't prevent knowledge. It defines its boundaries. It tells us where clarity ends and where possibility begins. And in that beginning lies not confusion, but creativity. Because when things are uncertain, they can change. The world is not a book with every line written in advance. It is a poem, unfolding, a dance, not a march. The more we understand this, the more we can embrace the idea that knowledge is not about holding tight to every detail, but about listening to the rhythm, the interplay, the emergence of form from probability. And so the more you know about one thing, the less you know about another. But that's not a loss. It's a gift. It's what makes reality breathe. If you're still awake, I hope your thoughts are softer now. The universe is stranger than we ever imagined, and somehow that makes it feel more forgiving. If sleep hasn't found you yet, there's another journey waiting. Just follow the link on screen or in the description and drift deeper. Thank you for being here. Good night and sweet dreams among the stars.